astronomy. And we're both in Dr. Robert's research group doing electrochemistry research. Today we're going to be showing you how to use the flat cell. Looking at with these flat cells is how the separator works in a supercapacitor. So in a supercapacitor you have these two electrodes that are going to be, one's going to be positively charged, one's going to be negatively charged. And these two electrodes are separated by a separator that allows ions to transfer from one side to the other and actually allows for this current to flow. And this is where you're going to get the energy storage to occur. So if we go and look at our flat cell over here, we're going to see that we have our device broken apart. We have our bottom, our top, our screws, and all that stuff. But the first thing we need to do is we need to place an electrode, and in this case we're going to use a carbon bucky paper electrode. And what we're going to do is you're just going to place it right in the middle of this smaller circle, because the smaller circle is where this actual testing is going to occur. And then what we need to do is we need to place a separator. And in this case we're going to use a woven separator of 40 millimeters. So we need to flatten it out, that way we can cover the whole electrode. Because if it doesn't cover this whole electrode, then we're going to cause shorting, because the two electrodes will touch each other. And these two electrodes touch each other, the shorting can damage the electrode. So it's important to make sure that does not happen. So anyway, we're going to put this little ring here that's just going to hold everything in place. And then we need the electrolyte in the system, or else the ions are not going to transfer. So we're just going to take this. This is just perchloric acid. We're just going to drop some in there, make sure that's good and covered with the electrolyte. And then we need to add the other electrode, because you can't have a supercapacitor without two electrodes. So we're going to take out the second electrode, which has been soaked in perchloric acid. And we need to rearrange it so that these two electrodes cover each other as much as possible. Because if these two electrodes don't cover each other, like if it's a bad coverage on this side, you see how the two shapes don't align, then you're not going to get as much current as we possibly can. So by overlapping these as much as possible, we're going to get a higher amount of current, which means that we're going to get to be able to use the maximum amount of electrode that we can. So again, we're just going to drop some perchloric acid on top, and then we're going to assemble the cell. So to assemble the cell, we have just this little metal disc, and this is going to provide uniform pressure over the top of it. But because of this way that this is concave down, we need to make it flat, and to do that we're going to use this stainless steel. It's just a sheet of stainless steel. And we use stainless steel because it causes no resistance. So that's so increased resistance would mean less performance of our cell. So we just need to place this thing right in the middle here. Then we're going to assemble our cell. So we have 4 of these screws. Just need to lock these things down. And then we have the top that goes on top of that. And what we're going to do once we're able to assemble this cell is we're going to be able to hook it up to our potential stat, which will be how we're able to test the performance of our supercapacitor and how it's actually performing. Because without the Versa Studio, we can't really determine anything about these supercapacitors. So we need to provide a second hookup, because right now this is only a 1 electrode system that can hook up right here. So to provide the second electrode hookup, we're just going to put just this metal connector there and screw it down. That way we can have a 2 electrode system when we hook it up to the Versa Studio. So we're just going to tighten this down a little bit. And this is important because if the supercapacitor isn't connected on top of each other really well, if there's not a strong connection, then it's not going to work as well as it could. It's not going to be maximized. So what this is going to do is we're going to put this down in this little hole here, and then we're going to screw this down on top of it. And what it's going to do is it's going to press down on that stainless steel metal square that we have, and then press down on the disc and provide pressure to the supercapacitor. That way we have a good contact. So to do that, we have to line this up down there. There we go. And then we're just going to screw this in on top of it. And once we have this together, we're able to hook it up to our Versa Studio. So if we're just looking at the wires here, the white is the reference, white on white is the reference, red on red is the counter electrode, and these two are the working electrode. So we're going to hook these two both to the bottom. But it's important when you're working with electrochemicals, things that you always attach the reference first and take the reference off last, because otherwise it can cause damage to your system. So we're just hooking up these two things here. And now that we have all of our four things hooked up, we are able to run it on the Versa Studio. But as you see, there's two places of contact, which is why we're calling this a 2-electrode cell. Hooked up to the Versa Studio, we're going to now run charge-discharge on it. So we have the charge-discharge system already set up, and what we need to do is we need to set the potential range that we want our flat cell to work under. So the bottom end of the potential range is basically when your battery would be at zero capacity, and the top of your potential range would be where your battery's at full capacity. So we're going to go ahead and set these potential ranges, and we're going to set it at 50 millivolts and 1 volt. So we need to set both of those. And then this is a constant current system. So we need to set the current so that the battery can charge and discharge. So basically what's happening here is you're going to see we're going to discharge the battery till it's at its 0 capacity, and then we're going to charge the battery. So this is like us plugging our electrical system into a wall. So we're getting current from an outside source. So the system is receiving current, so it's charging the battery up this curve. And when we get to the top, that's when it's at its full capacity. And then this would be like us unplugging it from the wall and just using the battery's energy. So this is, you unplug the system from the wall, and you're now using the current from the battery to power your system. So you're going to lose battery power. And this is when you get to the end, and then we're going to recharge it. So this just lets us calculate the capacitance and how our supercapacitor would perform if we put it into a real world system. So we're going to go ahead and run it. And what we're going to see here is that we're going to discharge the cell, the system, so that we will have we'll start our runs with the battery at empty capacity. So once it starts at empty capacity, we can see how it runs. So it's now at empty capacity down here at the 50 millivolts. And what we're seeing is that it's going to charge. So this is us charging the battery. It's like us plugging it into a wall and charging it. And once we reach this full capacity level, the system automatically switches to negative current, which is when you unplug the system from the wall and you start to use the supercapacitor's energy that's stored in it. So this is us taking current away, and we're seeing how the supercapacitor can perform when it's being used as an energy storage device. So from this, we can do some basic calculations, and we're able to calculate the actual capacitance of our system.
You guys how you use the cell. So pretty much a bunch of different parts down here. The first thing we want to do is take this white block and pretty much just stick it right here into the bottom of the flat cell. After that, you want to take in one of these stainless steel electrodes, because you need 2 electrodes in your system to actually conduct something. You want to put that in the bottom and just make sure that it's in the center. And then you take one of these 3 spacers that are right here, and we have 3 different spacers. One that's 0.5 millimeters, 1 millimeter, and 2 millimeters in length. And that's just to separate the two electrodes so that you don't have a short happening in your circuit. So you'll pretty much just take one of these spacers, put it in the middle, just make sure it's down all the way. And after that, you take your solution, and which in my case is a solution of polymer in an ionic liquid. You just get a pipette, take some out, and what you're going to do, you're going to pipette right here into the middle where the spacer isn't touching the electrode, and just make sure that that entire middle part is covered up with liquid. Once you're done with that, you can take the other electrode, stick it right on top of it, and then just add a little bit more electrolyte solution on top just to make sure that it's completely covered, like so. Then again, just make sure that's in the middle. Then you take this other, just kind of separate it, just to separate the electrode from everything else. And after that, it's really just a bunch of screwing things together. So you're going to put this together, screw that, and then take the screws, put it all together. Quickly go over how we kind of measure things using the system that I set up using the polymer electrolyte. So as you can see here, if you look at this graph, you pretty much have a voltage right here, and the straight line right here represents a DC voltage that you're putting through. And then the little sinusoidal graph that you have right here shows the AC voltage that you're putting through. And in response to the AC voltage, you have an AC current that's going through, which is this graph right here. And the main thing that you want to notice from this is that the voltage and the current are not in phase anymore, they're out of phase, and this leads to impedance within the system. And you use this impedance to calculate the solution resistance, and once you get this resistance, you can then calculate the conductivity. The safety aspect of using these flat cells is making sure you dispose of your waste correctly. So as you can see here, we have a couple of different solutions that we use, and one solution that Bobby used was the TBAF and propylene carbonate. And so since this is non-aqueous solution, we want to put this in the non-aqueous waste. So to do that, you uncap the bottle containing the non-aqueous waste. You take your non-aqueous waste and you pour it down, making sure you get all of it out. And after that, you just cap up the non-aqueous waste container, making sure that it's not too tight or else the bottle will explode. This video was prepared as part of the National Science Foundation REU on National Advanced Functional Membranes at Clemson University. Thanks for watching.